Lecture 23 covers sections 6.10 through 6.11. At the end of today's lecture, you should be able to understand and apply the increase of entropy principle and the entropy balance equation for closed systems. To develop our entropy balance equation, let us consider two processes: an irreversible process that we take going from state 1 to state 2, and a reversible process that we take going from state 2 to state 1. We can express this as the integral from state 1 to state 2 of delta q per t for an irreversible process, plus the integral from state 2 to state 1 of delta q per t for a reversible process. We're going to say this is equal to minus sigma. Sigma is our entropy production term, and it indicates the strength at which we produce entropy. Our book calls this S-gen. A reversible process is simply the change of entropy between states 2 and state 1. That is, we can re-express our first equation as S2 minus S1, i.e. our change of entropy, is equal to integral from state 1 to state 2 of delta q per t for our irreversible process. We're going to call this term entropy transfer, plus sigma, our entropy production term. And this equation is our entropy balance equation for a closed system. If we look at this equation, the first term on the right-hand side is the entropy transfer associated with heat transfer, our delta q per t, for an irreversible process. And this follows the sign convention associated with heat transfer processes that we've used thus far. Thus, we can say the second term on the right-hand side is a measure of our change of irreversibilities, other than those associated with heat transfer processes. That is, S2 minus S1 can be equal to our entropy transfer plus our entropy produced. If there is no entropy transfer due to heat transfer processes, we can still have entropy production that allows for us to calculate a change of our entropy between our final and initial states. Now, sigma can take three possibilities. Sigma can be greater than 0 when irreversibilities are present. Sigma can be equal to 0 when there are no irreversibilities. And sigma cannot be less than 0. Conversely, our change of entropy, S2 minus S1, is bounded between negative infinity and positive infinity. That is, we can have three unique situations occur. S2 less S1 can be greater than 0 for when entropy enters our system. That is, we are having an increase of entropy associated with heat transfer processes. S2 less S1 can be equal to 0 when there is no change of entropy. That is, there are no irreversibilities and no heat transfer processes within our system. And S2 less S1 can be less than 0 when entropy exits our system. Now, let us consider a modification to Joseph Black's experiment on determining specific heat. Say we have saturated liquid water at 100 degrees centigrade contained within a piston cylinder setup. If the piston cylinder is frictionless, the cylinder is perfectly insulated, and energy is put into the system via the use of a paddle wheel. Until our liquid becomes a saturated vapor, we want to determine the increase of entropy per unit mass basis. To do this, we're going to look at our entropy balance equation. S2 less S1 would be equal to integral from state 1 to state 2 of delta q per t plus sigma. Since there are no heat transfer processes associated with this, i.e. our cylinder is perfectly insulated, our change of entropy between our final and initial state is going to be equal to sigma. Or, on a per mass basis, sigma per m would be equal to S2 less S1, i.e. Sg minus Sf for liquid water existing at 100 degrees centigrade. Or, on a per mass basis, our entropy production would be 6.048 kilojoule per kgk.